We are in Chapter 7, Estimating Parameters and Determining Sample Size. Section 7.1 is Estimating a Population Proportion. This section presents methods for using sample proportions to make an inference about the value of a corresponding population proportion. So first thing that we have is called a point estimate. And the point estimate is a single value used to estimate a population parameter. And the two parameters that we're going to be talking about is proportions. So our point estimate is p hat, and the mean, and our point estimate is going to be x bar. The sample proportion p hat is the best point estimate of the population proportion p. So p hat is an unbiased estimator of p. Next definition we have is confidence intervals, or an interval estimator is a range or an interval of values used to estimate the true value of a population parameter. We have what's called a confidence level. It is the probability, we call it 1 minus alpha, this is going to be something like 0.95 or 95%, that confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. Alpha is called the degree of confidence, or our confidence coefficient. An example of a correct interpretation of a confidence interval would be we are 95% confident that the interval from 0.405 to 0.495 actually does contain the true value of the population proportion p. And we use confidence intervals all the time. A lot of times when you're done with an exam, you will walk out of an exam, you'll be like, I'm pretty confident I got a B. Well, maybe I got between like a C plus and an A minus, but you kind of have a range of values that you think that you might fall between. And so that's the same idea with this. So the example that we have here says a USA Today Gallup poll asked 1,006 adult Americans how much it would bother them to stay in the room on the 13th floor of a hotel. Interestingly, 13% said it would bother them. The margin of error was 3 percentage points with a 95% confidence. Which of the following represents a reasonable interpretation of the survey results? For those not reasonable, explain the flaw. So there's 4 here. Only one of them is the correct way to write our conclusion. The other 3, there is a flaw with them. So take a second to look through those. Easiest thing to look for first is the ones that are incorrect. And so when we have this problem on this, it says that there's 13% are bothered to stay on the 13th floor and in a hotel room. And it says the margin of error is 3 percentage points. So what exactly does that mean when it says the margin of error? Well, what that means is that it's like a plus or minus. So our 13% that we have, there's a plus or minus. There's an error of 3 percentage points. And so this means that our value would be somewhere between 10% and 16%. With that adding and subtracting of that 3 percentage points of our margin of error. And so it says, what is a reasonable interpretation of this survey result? So let's look at B. So this one says that the confidence is changing. So we are between 92% and 98% confident. That doesn't change. Our 95% confidence is sound. Does not change. We are staying 95% confident. So this is not correct. And the reason why is this interpretation indicates the confidence changes. And the confidence doesn't change. That is still set at 95% confident. Another one that we have that is not correct would be D. If you look at D, it says we are 95% confident that 13% of adult Americans would be bothered to stay in the room on the 13th floor. This one does not talk about the margin of error at all. So this one is also not correct. And it doesn't have an interval for us, so we have no margin of error or no interval. Okay, so we have it narrowed down right now to A and C. So looking at the two of these, if you notice that 95% is our confidence level, and if you notice with C, it says 95% of our samples, and so this is not correct. And so reason why is because that 95% is our confidence level. And so that means that A is correct. So looking at A, it says we are 95% confident that the proportion of adult Americans who would be bothered to stay in a room on the 13th floor is between 0.10 and 0.16. So that's a correct interpretation of that conclusion that we would have. So at the bottom of the page it says a confidence level of 95% tells us that the process we're being performed in the long run results in the confidence interval limits that contain the true population proportion would happen 95% of the time. So on the next page it says suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. Then our sample proportion, our p hat, is defined by x over n, where x is the number of individuals with the sample with a certain characteristic, and the sample proportion p hat is a statistic that estimates the population proportion p, and n is also the number of people in our survey, or however many individuals that we're surveying, or animals, or whatever it is that we're dealing with. So the example on the page says in a town of 500 households, 220 have a dog. The population proportion of dog owners in this town expressed as a decimal is going to be p hat. And so p hat for us is going to be the number of individuals that have a dog, which is going to be 220, divided by our sample size, which is 500 households. And it wants us to express this as a decimal. Let's go ahead and just round it 2 decimal places. So we get 0.44. There's a little note down there that says, note, a second survey of 500 households would likely have a different estimate of the population proportion of households that own a dog. Because the value of p hat varies from sample to sample, it is a random variable and has a probability distribution. So we talked about in the previous section, or previous chapter. To get a sense of the shape, center, and spread of the sampling distribution of p hat, there's a list of things that we can do to kind of get that figured out. Next definition we have is a critical value. Is the number on the borderline that separate the sample statistic that are significantly high and significantly low from those that are not significant. So remember, significantly high and significantly low. So we have these cutoff values that would cut these from the values in the middle that are not significant. So for example, a 95% confidence, or alpha equals 0.05, implies that if 100 different confidence intervals are constructed, each based on a different sample from the same population, then we would expect 95 of those intervals to include the parameter and 5 not to include the parameter. So 95% of the time the parameter will be included in the interval. And this is something that MyOpenMath talks about a lot in their conclusion writings and interpreting the confidence intervals. So 95% level of confidence does not tell us there's a 95% probability that the parameter lies between the lower and the upper bounds. And 95%, you guys can see that that confidence level is the middle part of that graph, because that's the part that we're confident about. There's always things that are going to be smaller than it and then also larger than it that we're not as confident about. The table here is very nice to have and to use. These are the most common levels of confidence that we have. So that's 90%, 95%, and 99%. This does not guarantee that these are the only ones we're going to have, but because they're nicer, they're written in a table for you guys to kind of use. So if you look at the confidence level, you have 90%, 95%, and 99%. That value for alpha is going to be 1 minus that confidence level. If that confidence level written as a decimal, so this is 1 minus the confidence level. But again, write down as a decimal. And then getting these critical values, which is Z alpha over 2. And so to calculate the critical value for a 98% confidence level, so this is one that's not on our table, so I want to go through this because, again, not always are these confidence levels going to be 90, 95, and 99. They can be other values. So in order to do this, I'm going to go ahead and draw my bell-shaped curve just to kind of get a visual approach on this. So drawing my bell-shaped curve. It says that we are for a 98% confidence level. So that 98%, my right in the middle is going to be 0.98. And so that means that I have, because a bell-shaped curve or a normal curve is symmetric, each of those tails is going to have the same amount of area underneath that curve. And so if you do 1 minus 0.98, you get 0.02. But because it's getting split into 2 sections, and divide by 2, and we get 0.01 will go in each of these tails. And so since we are dealing with our standard normal curve when we deal with this, I'm going to go ahead and call this one Z1 and this one Z2. And so the standard normal curve, we have that the mean is equal to 0, and our standard deviation is equal to 1. And so in order to calculate our Z1 value, we are going to use inverse norm. And inverse norm is going to be the area to the left, which is going to be 0.01, comma the mean, comma the standard deviation. And then to calculate Z2, we use inverse norm. And then going and looking at the area to the left of this value, that would be this 0.98 plus the 0.01, which is going to be 0.99, comma the mean and the standard deviation. Remember that this is a symmetric curve and that those two, the Z1 and the Z2, those two values should relate to one another. So try on your calculator to come up with those two values. Let's go ahead and round 3 decimal places. So from the calculator, we get negative 2.326 and positive 2.326. On the next page, it says requirements to create a confidence interval for estimating a population proportion, P. First thing is our sample needs to be a simple random sample. The conditions for the binomial distribution are satisfied, and this is back in section 5.1, so if you don't remember that, go look it back up. And you need to verify that the normal distribution is a suitable approximation for the binomial distribution by verifying that n times p and n times q are both greater than or equal to 5. So this is what you guys would have to check. It says the higher the level of confidence leads to a wider interval and a larger margin of error. So the margin of error we've discussed, but we never really had a definition yet. We call this capital E. Is the maximum likely amount of error between the sample proportion p hat and the population proportion p. It is also called the maximum error of the estimate and can be found by, so we have a couple different formulas here depending on what is given to you. And so the error is going to be the upper bound minus the lower bound in your confidence interval divided by 2. And then another way to use this is Z alpha over 2. And Z alpha over 2 are found either in the table here, this is what Z alpha over 2 is, or by what we did in the example right below if it's a different value rather than 90, 95, or 99%. And then we multiply by the square root of p hat times 1 minus p hat, all divided by n. It says note that a confidence interval about the population proportion is of the form p hat plus or minus e. The point estimate p hat is the midpoint of the upper and lower bound, and the margin of error e is the difference between the point estimate and the lower bound. So we have a few different formulas that we're going to add in right here. So first one that we want to take a second to look at is that it says that that point estimate, if you add and subtract your margin of error, is where your proportion would be, your true proportion. And so this p hat, you would minus and subtract e, and p hat plus e to get that upper and lower bound that we have. So again, subtracting E from your true proportion and adding E. And another way to express this is a trilinear equation. So we have P hat minus E and then P hat plus E. So this is a trilinear equation. And so another way to be writing this is also as what was written up above, P hat plus or minus E, or the way that the calculator writes it, which is going to be P hat minus E, comma, P hat plus E. Okay, it also tells us that the point estimate P hat is the midpoint of the upper and lower bounds. So we'll go ahead and write that equation down also. So P hat is the midpoint. So that means we're going to add our upper bound plus our lower bound and divide that by 2. So that's going to go ahead and give us our P hat value. So the next example says express the confidence interval using the form P hat plus or minus E, round 3 decimal places. It says the confidence interval for the proportion of red M&Ms is, and it gives us this value here. So if you notice, we have our upper and lower bounds. So this is our lower bound here, and this is our upper bound. But we don't have P hat and we do not have E. So in order to get your P hat value from, and this would be the way that the calculator gives you your answer, so if you ever need to get the P value, the P hat value, you're going to take these two values that we have, and from up above, we're going to take the upper bound and lower bound and add them and divide by 2. So 0.217 plus 0.0434 divide by 2. And we get a P hat value equal to, and again it says round 3 decimal places, so 0.130. And then we also need to come up with our margin of error, and that is up above and it's typed. And it says it's the upper bound minus the lower bound, all divided by 2. So your upper bound is 0.217 minus the lower bound, and then all divided by 2. And when you do this and we round 3 decimal places, we get 0.087. So from this, it wants us to express our answer in a certain way. It says it wants it written as P hat plus or minus E. So P hat is 0.130 plus and minus E, which is 0.087. And so again, the way that your calculator gives you answers is going to be expressed as lower bound, comma, upper bound. So the next thing that we have on here is constructing a confidence interval for a population proportion with a TI-83 or 84 calculator. So first thing is, a lot of times it's going to ask you guys for your point estimate, which is P hat, which is going to be X divided by N. Then you have what you need to verify. And then for our testing, we go to stat, test, and then for me it was A. If it's different on your calculator, change it. And we go to one prop Z int, which you're going to be asked to enter in X and N values. You're going to enter your confidence level, which is called C level, highlight calculate, and select enter. And when you do this, it's going to give you a lower bound and an upper bound, or a lower limit and an upper limit. And then we're going to interpret our result. So on to the next page. This one I'm going to go ahead and circle, and we'll look at it later and together. The next thing on here says, as the sample size increases, the results is a narrower confidence interval and the margin of error decreases. So definitely something that would be good to know. And the next box underneath that says sample size needed for estimating the population proportion P. So when an estimate P hat is known, so when we know a prior estimate, maybe a study that somebody else did 10 years ago or 50 years ago or 3 years ago, we're going to use the formula N equals Z alpha divided by 2 squared. times p hat times q hat, all divided by e squared. And it says rounding up to the next integer. So you need to round up always to the next integer. So p hat we know is our point estimate, and q hat is found by doing 1 minus p hat. And then also the value of z alpha over 2 is from that table on the very beginning of the notes, or you can calculate it by hand if it is something different than 90, 95, or 99%. There's a second formula on here. The second formula says when no estimate p hat is known, our formula is going to be n equals z alpha over 2 squared times 0.25 divided by e squared. And again, you're going to round up to the next integer. And so this is when no one has maybe done a study, or you have no estimate about what the study is even about to go based upon. So the next example says find the sample size needed to estimate the percentage of California residents who are left-handed. Use a margin of error of 3 percentage points and use a confidence level of 99%. So we're asked to find the sample size, and sample size is n. And so sample size would be finding your n value. And part A says assume that nothing is known about the percentage of left-handed residents in California. Whereas B says assume that based upon prior studies, about 10% of Californians are left-handed. So that's when we actually know something a little bit more about our study. So I'm going to go ahead and look at A, where it says assume that nothing is known about the percentage of left-handed people in California. And so since we don't know anything, I'm going to be using the second equation on here. I'm going to go ahead and copy that down. And so we have n equals, and it's z alpha over 2 squared times 0.25, all divided by e squared. And in order to get our z alpha over 2, we are going to go back and look at our table since we are dealing with 99% confidence. And at 99% confidence, we have our z alpha over 2 value is going to be 2.576. So I'm going to go ahead and copy that down for our problem. And it's squared times 0.25 divided by E. And E is our margin of error. So careful here because it says 3 percentage points. So that means E would be equal to 3 percentage points, which would be equal to 0.03. And so we're going to square that. And then substituting all this in on your calculator, we get 1,841.84. But remember, it always says to round up. So we are going to round up for this. And so with rounding up, we are going to get a value of 1,842. And we are serving Californians, or we can put down just people. Part B is the same problem, however, Part B is asking for us to assume that based on a prior study, about 10% of Californians are left-handed. So instead of using that second equation, we're going to actually use the first one. So I'm going to go ahead and copy that down. And so we have n equals, and it's z alpha over 2 squared. And we have p hat times q hat, all divided by e squared. And so our p hat value is that 10%. Our z alpha over 2 is the same value that we had for part A. So I'm going to go ahead and copy that down. That was 2.576. And then we have p hat, which is going to be 0.010. And then q hat, which would be 1 minus 0.10, or you can write that down as 0.90. And then we're going to square r is the alpha over 2 and square our e, and the error is still the same. So that would be written as 0.03 squared. Substituting all this in on your calculator, we get a value of 663.06. But again, remember, we always round up. So rounding up, this is going to equal 664 Californians or people. And that's how many total people we would need to survey. Always, always, always for sample size, we're going to round up for this.